TGIF, everybody. How are you today? It's beautiful. It's not very hot, not very humid. There is a tropical breeze. And I have been getting some good night's sleep, so I'm feeling fantastic, thank you. How about you? Getting sleep? So, as some of you may or may not know, I'm a science geek, and beyond that, I am obsessed with geometry, fractal geometry specifically. Oh, I better not do that. And how it relates to nature and the universe. The more I learn, the more fascinating it is. It's a wonderful thing. So large is my fascination with fractals that I pretty much committed myself with the free time that I have to have my digital paintings, my artwork all be based on fractal equations and geometry tied with music, which I also find out that has direct correlations to fractal equations, which is way cool. So I'm exploring that, looking to see what those relationships are. So where do I start with fractal geometry? Well, let's maybe look at the history of it. Typically, we had Euclidean geometry, which is based on Euclid and Plato, and Platonian shapes, which is basically your square, hexagon, triangle, two-dimensional planes, and back then, time of Plato and Euclides, I don't know how to say that in English, Euclid, back in the time of the Greek philosophers, it was thought that 5 to 12 basic shapes described all of nature, and we find that not to be true now. What we find is a more complex variation. Nature is really closer to fractal geometry and four-dimensional complex shapes than it is to Euclidean geometry. And the first person to really think about it in detail and have the tools to figure it out was Benoit Mandelbrot. Mandelbrot was trying to figure out why coastlines and why trees had imperfect shapes, seemingly imperfect shapes, and why these shapes had irregularities And he derived a formula which is your typical the Mandelbrot formula, which is basically a mathematical recursive formula that adds a number to the loop every time it loops, and that number creates these recursive patterns, and as the number increases, the pattern gets larger. So from one or two loops, when it gets into the hundreds, that pattern becomes something, makes shapes that are very, very similar to shapes in nature. And what we find is that nature has certain equations built into it that many, many shapes in nature follow. One equation is phi, phi, and phi is what is commonly called the golden ratio. That golden ratio is basically 0.618, or roughly taking a square and dividing that square roughly 2/3 into 2/3. You draw a line. Now you have one square or one rectangle. And the beauty of it is, if you use the Fibonacci sequence, you can keep on going infinitely to make smaller and smaller squares and rectangles. And here's one perfect example of something that follows that math. Think of a nautilus shell. So a nautilus shell is a perfect golden ratio, and it increases its size on a perfect Fibonacci scale. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus, so it keeps on going, 5, 8. So it turns out that many, many things in nature and in the universe follow phi and follow the Fibonacci sequence. And at a universal scale, there are certain constants that are also prevalent everywhere in nature. One of the greatest constants of all is the speed of light, which I think is like 286,000 miles per second kind of thing. Sorry, I don't know the metric equivalent, but that'll have to do. So we have these constants. What is interesting about this constant, the speed of light is one of the very few constants in the universe, is that if we were to say that we're living in a computer simulation, that number would correspond to the megahertz, or the CPU crystal time of a CPU chip. And there are so many parallels of computers, pixels being atoms, the speed of light being the CPU clock speed, on and on. That's a little unnerving for me. But getting back to fractals and its connection with nature and what have you. So Mandelbrot came up with this equation that it is recursive and self-similar. And actually, let's just talk about some things in nature that have mathematical equivalents and things that we don't see, we fail to notice in our everyday lives that are so interesting. You ever seen a Romanesque broccoli? Well, Romanesque broccoli is perfectly a Mandelbrot fractal. It's within the smaller little branches of a Romanesque broccoli is the same design as the larger one. It follows phi, it follows Fibonacci sequence, and even the tiniest one will have the same design as the overall look at it. And you're limited only by quantization, or in other words, as you become smaller and smaller, you start getting pixelized. Hold on a second. Oh, this is a cul-de-sac. Oh, no, it's not. Goody, goody. So, as you look at the smaller and smaller versions of it, it becomes pixelized. And interesting, again, is the correlation to computer graphics and the loss of resolution. As you go in, zoom in further and further, it becomes more and more pixelized, right? That's an interesting analogy, something to think about. So, Google Romanesque broccoli and you will see it's almost like a 3D printer generated a Mandelbrot fractal and created this shape which is made by nature. Another beautiful, beautiful geometric pattern found in nature that is also phi and Fibonacci is the center of a sunflower flower. The sunflower has a Fibonacci spiral and it is flipped. It has a clockwise Fibonacci spiral and a counterclockwise Fibonacci spiral. And that's why you see the seeds certainly look like they're going in two directions. And the leaves, the proportions of the leaves to the center, to the outer rim follows the golden ratio, which is 1.618 or 0.618 depending on the scale. So that fascinates me, that we have these magic numbers that apparently have been used to create so many shapes and forms in the universe and in nature. There is basically what is called the golden ratio angle, and that's 27.3 and a couple of other digits after the 3, but that angle occurs naturally in so many places in nature. It occurs in the vestiges of when waves hit the shore on the sand and retreat. If you measure up the angles of the lines that are being created, the ripples, most of them measure 27.3, which is the phi angle. Fern trees are amazing. Fern trees follow the Mandelbrot fractal, follows the golden ratio, which is phi, and follows Fibonacci sequence. So if you look at a fern tree and just plot an angle from the top of the cone of the tree to the bottom where the leaves, the branches are the whitest, it measures, guess what? 27.3. The angle is 27.3. If you take a branch and you measure the beginning of the branch where the branch is the whitest to the tip of the branch, guess what? 27.3 again. If you take a leaf of the tree and you measure the leaf from the widest point to the tip, you got it, 27.3 degrees again. Now that's one beautiful correlation. I'm not going to call it a coincidence because it's a correlation. The other beautiful correlation is that the whole fern is another perfect Mandelbrot fractal. Now this is the Julia fractal, which is a little different. The Mandelbrot is kind of a bubbly circle and ovals, but the Julia fractal creates trees. And in the case of the fern, it is self-similar in that, just like with the Romanesque broccoli, the overall tree has a shape and a structure of how the branches look, but you can take one of the branches and it looks just like the tree. It has the same structure, the same design as the overall tree. Take a leaf from that branch, and when you look at it, you got it. It looks like the branch and it looks like the tree. Self-similarity. So I think Mandelbrot did for natural shapes what Einstein did for time and space with the theory of relativity. He really broke through the prison, the Euclidean geometry prison that we were living in, and said, hey, nature is not imperfect and not chaotic. It follows mathematical rules that are beautiful and self-similar, and has these beautiful ratios like the golden ratio and the Fibonacci sequence. When you add it all up with Mandelbrot's equations, you can create clouds, you can create trees, you can create mountains and landscapes. And with modern landscape software like Vue, V-U-E, you would not be able to tell. I could make a Vue landscape that's generated in a computer that you would not be able to tell that it's a computer-generated landscape. It's simply, we figured out the mathematical equations that generate all of the shapes in nature. That's amazing, guys. The fact that our tiny 3-pound human brain can even comprehend the architecture of nature and the architecture of the universe and the origin of the universe is a huge thing. It is huge that we're able to comprehend these things. The other beautiful concept here is that with everything we know in the 21st century, the year 2019, we are still just as a child, a 5-year-old child staring at the New York Library in awe of all the information there and how little do we know as that child compared to the knowledge that is stored there. That's where we're at. There's so much more to learn. So, I've been spending my free time. Summers are very slow for my business, and it's been slow. This has been one of the slowest summers I've had, and it's all good. I'm about to retire, so it's all good. But since I have the extra time, I've been plugging these equations into little programs that I've custom written, and the program plots the equations into forms, and it looks like a painting. And just the fact that it makes these beautiful paintings out of mathematical equations is amazing. But more so is that as opposed to a two-dimensional painting that I paint, that I could not zoom into the painting or do like a Google Maps, Google Earth, and keep on zooming in to the territory. With the fractal painting is alive, and it has dimensions. It's 4-dimensional actually. It's 4-dimensional that folds, collapses into 3-dimension, and those 3-dimension collapses into 2-dimension, so you could actually see it without 3D goggles. So wow, there's another tennis court here. So I'm amazed at what comes out. It's a whole universe in itself. I could zoom in to any point, and the more I zoom in, the more details of this world inside of math I uncover. And I could actually animate it. I could animate my journey through the top of the drawing into the middle and zooming around like a rocket. And that's what I've been working on. What I'm finding is the computational power and graphics card power it requires for merely 30 seconds of this kind of animation is way beyond the power of the computers I have at home. So kind of saving up some money so that I can afford to get a computer that is a true, think of it as a hot-rodded gaming computer. That's the way it would have to work for a Bitcoin mining machine, where it's all driven by the graphics processor unit. So the new machine would have to have two very good graphics cards, like a NVIDIA T1080, like dual of those, or a Radeon RX 580. I need at least two video cards with an 8-core Ryzen CPU, 60 megs of memory, and an SSD hard disk to run these computations, because literally for 30 seconds it took me the other day for a small, like 900 pixel animation, 30-second animation at 30 frames per second. It took me the better half of the afternoon and night. I basically had to leave the computer running until it did 900 frames. Basically, all it does is it produces 900 images, which you still have to grab and throw into a video editor and set up timing between each frame and save as an animated video or a GIF. That takes half a day, literally. So that's a little tough, because you lose that real-time inspiration you have, that you're working with things, you want to see how it looks, to then just go right back and make changes. So we talked about phi, and we talked about phi, the golden ratio, and the Fibonacci sequence. So many flowers are generated by Fibonacci sequences. That's so beautiful to me. And at the macro level, at the macrocosm level, at the universal level, the other constant, we talked about the speed of light being one constant, but the other constant is the iterative fractal series, the find constant, the iterative find constant, and that is a constant that it is built in to the elements, the table of elements. It's built into the construction of the planets, and to everything at the large level, at the macro level. So we have that, it's amazing for me that we can find these correlations in everything in nature and everything in the universe. So I've been fascinated with that, and I've been plugging these numbers into different programs. Which, by the way, I wrote a program that picks ladder numbers. If you're interested, message me on Facebook. I'll be happy to share it with you. To see that math can produce beauty. Math produces beauty when we utilize the equations that generate fractal geometry. That's mind-blowing for me. That is absolutely mind-blowing that you can give a computer mathematical equations that loop, that are recursive, and add a little variable every time, and out of that, after a couple of hundred loops, you create a beautiful, beautiful image. And not only did you create a beautiful image, you created a geographical map that exists in the mind of the computer. And you can tell that map, hey, I want to fly in 300 times, and the computer will gladly oblige and zoom you in 300x, and you're still inside this world. And who knows, that may well be how nature behaves. Oh, again, here's a beautiful thing about nature correlating to us being in a computer program. The Heisenberg's uncertainty principle and the behavior of particles and waves is that when you're not observing matter, it behaves like a wave. And it's a wave of probabilities, and a basketball can exist simultaneously in at least 32 positions. It is only when you look in the microscope and observe that quantum wave collapses into a given spot, a given place, and the basketball appears in one place. And that is one of the most perplexing qualities of quantum physics. That when you're not looking at it, it exists as a wave of probabilities. But when you look at it, it appears in one given space. What is interesting is that is exactly what happens in a video game. When you're inside a video game, what you're viewing at that point, you're standing in a video game and your character, the computer only gives you what is visible to your line of sight. It is only when you move and you turn around your character that the computer presents you with the next scene or zooming into whatever. So there are a lot of parallels of nature, how it behaves, quantum physics, and computer games. And with that, I'm going to say bye because I'm already too tired and it's too hot. And guys, enjoy your weekend and wonder about this marvelous world and universe that we are privileged to be a part of.